Let's begin. Um, Today we will wrap up our study of selection. Last time we went over a randomized algorithm for selection. It seemed quite intuitive, and we looked at various recurrence relations that were motivated out of that. At the end of the class, I will talk about recurrence for randomized selection. It will be a very different kind than what we have seen, but we will just quickly review that. But before that, I want to go over a very clever design divide and conquer algorithm, which is deterministic, which does not use any randomness for this selection problem, for basically the problem of finding the median of an unsorted list. So after merge sort and the randomized algorithm for selection, this is sort of the next another example of the divide and conquer algorithm. We will move on next in our next class to yet another example, that of finding closest pairs of a given set of points. That would be another example of divide and conquer, and that will basically complete our study of divide and conquer. Okay, so let's recall again what the selection problem was. The selection problem is that you're given an array of n elements in not necessarily in sorted order, in an arbitrary order. And our goal is to find, and you're also given a number k, and goal, the output, is find element of rank k. Okay? So that's the problem, and a prototypical example of this is to find the median, the midpoint. Okay? We know how it's very easy to find the rank 1, it's very easy to find rank n. The median seems, at least the ideas that we know, do not seem to apply. And you can imagine finding 25th percentile, 75th percentile, various statistics, order statistics are very useful in this situation. Okay, so now we need to do this. We saw one way of doing it, which was randomized selection. And the randomized selection was basically pick a random pivot element, partition around the pivot, recursively recurse into the side which has the element we're looking for. Desired rank. Remember that? Right? So we pick a random pivot element, and that way we split the array into two parts. If you're very lucky, we get exactly half-half, then we break our problem down into size half. If we are very unlucky, then we get n minus 1 and 1, but we believe that that's very unlikely to happen. So we hope that most of the time we are in a situation where we bring down the size of our problem by a constant. And if you remember, whenever you have a recurrence of the following form, T of n equals T of, let's say, alpha times n plus n, where alpha is a constant strictly less than 1, this recurrence will always lead you to the bound T of n equals theta n. Okay, and just intuitively, what's going on when we solve the recurrence relation for this? At the top level, you will have a contribution of n. At the next level, you have a contribution of alpha n. At the level below, you have a contribution of alpha square n, and then alpha cube n. And alpha is strictly less than 1. So if you add up all of these, you get a geometric synchronicity going to infinity, but it's bounded by a constant. You get the
In randomized selection, we're assuming that the array that we're given is sorted.
No. If the array was sorted, then you could find the element in just one lookup. Right? You have to find the element, the median element. If I give you the array in a sorted manner, you would simply look up the middle element and return that element.
So then I don't understand how, if we're taking a random pivot and
Yeah.
partitioning it.
Partitioning is not easy. You compare every element to that pivot and put the lesser elements on one side, put the bigger elements on the other side.
We're sorting it.
Not sorting.
it, but like we're putting the less elements.
Absolutely. So this is where all the action is. This is why it's taking this n is because of that. Okay? This n is the time for partitioning. Okay? Okay. So that's our aim. So why are we so obsessed about trying to get linear time? Well, we know how to sort. Okay. So we could always sort it. If we sort it, we would get a running time of theta n log n. Which is not linear time. It goes a little bit more than linear time because it's not going the same as n, it's going a little bit more than n times. So our question is the problem of finding the median easier than problem of sorting the whole thing? You agree that if you sort the whole thing, that there's nothing much to do. You can just look up the element if you want. But if all you wanted to find was the median, you didn't care about sorting it exactly, can you do that faster than? Okay? And so far we don't know how to do it. We have this randomized algorithm that seems to be quite likely that it will do the right thing. But so far we do not know whether this will work out. Okay, but the intuition that we have is if we can find a pivot that is that splits the thing roughly evenly, then we are in good shape. Okay. Okay. So one strategy, of course, would be let me find a pivot that splits the array into two even parts. Okay. What is the pivot that splits the array into two even parts? The median. So now it's a circular problem. In order to find the median, I'm saying let me actually first find the median to split it evenly, and then so that goes. But remember, we don't want it to be completely even, as long as even it's roughly even. So here is the key idea for a deterministic algorithm. Find a useful pivot without sorting the whole thing, because of course if you're sorting then you've already lost the game, and without finding a median, because that's what you started off with solving. So somehow find a useful pivot fast. How do we do that? Okay. So this is a really beautiful algorithm that was developed in the late 70s. And it's actually, the idea behind this algorithm is I will identify certain elements. I'll take a much smaller subset of the elements. and recurs on that to find a useful pivot for the bigger set. Okay? I'm going to give the algorithm for the pivot, and then we'll put down the whole algorithm on the board, and then we'll go ahead and analyze it. Okay? So let's say we did the following. We took all the n elements, and I write down these n elements here. And I group them in groups of 5 elements. Don't worry about why 5. Okay, there is a reason for it, but you will look at some of that. Okay? So I've taken the n elements, and let's assume for now that it's evenly divisible by 5. It's not that necessary. If there were a couple of extra elements, that's not it. Okay, so I've written them like this. Okay. I take each of these 5 elements, and let's say I sort these 5 elements. Just the 5 elements. These 5 elements I sort them. Then I sort these 5 elements. Then I sort these 5 elements. Then I sort these 5 elements. So on. Okay? So I've sorted this 5 elements. So let's say the way we are sorting is upward is larger. So let me draw the arrow like this. So this is the largest. This is next large. This is next large. This is okay. How long did this process take? How long does it take for me to sort 5 elements? So you might say 5 log 5. It's some constant time. Okay? You could even compare all pairs if you wanted. If you compare all pairs, how many comparisons do you need? 5 choose 2, which is like 10 comparisons, and you could go ahead and do that for everybody. So you compare all pairs and you sort them all. So this will take you about, I don't know, 10 units of time. This will take you about 10 units of time. You're doing it for how many groups? N over 5 groups, because there are n, and n over 5 times 10, so you get 2n. That's linear time. Okay, so how much time did it take you to do this grouping and sorting? Grouping and sorting time. Okay. So now is the key part. Look at these middle elements. How many middle elements do you have here? N over 5 middle elements. Okay? Now let's not think about algorithmically, let's do a thought experiment here. Let's suppose I arrange these groups in such a way that this is, so what was I assuming? That this is greater than this, greater than this, greater than this, and so on. Let's say things are greater than, so this is, okay, so up is greater, let's say right is greater. Let's say I arrange in such a way that this is bigger than this, which is bigger than this, which is bigger than this, which is bigger than this. Okay? Yes?
How do we know that it's going from smaller to larger?
It is not. So I'm saying, don't think algorithmically. Let's suppose we take and arrange all of them. for the time being. Okay, a very good question. What if you decide that we are going to sort them? Okay, then you have n over 5 elements and you're going to sort them. How much time will that take? It will take n over 5 times log of n over 5, but 5 is just a constant, so for large n, that's just theta n log n. So that will be complete waste of time, all the circles we did just now, because ultimately we are just sorting. So we cannot do that. Okay? But for now, allow me that look in this picture, let's just arrange them in sorted order. Okay? And there is a reason I'm doing this. Okay? So these are all the medians of these groups of 5, and I've arranged them in sorted order. Let's look at the middle element of this. Okay? The smack in the middle element of this. So let me call this element M, which is the median of medians. Okay? So it's clear so far what's going on? Okay. Now, question for you. Let's try to understand how the rest of the points look with regard to when compared to this median. Is this element greater or smaller than this middle element? Smaller. This one? This one? Is this element greater or smaller than this middle element?
We don't know.
We don't know. Why is that? Well, all of these are smaller for sure, but this is bigger than this, and that's all we know. Okay. All right. Good. What about this element? Smaller. This element? What about this element? Smaller. So, which portion of this rectangle here is guaranteed to be smaller than this? The left quadrant, right? Okay, I mean, I should not include this point itself, but very clear? Everybody sees that? Okay. What about the bigger ones? Okay, that's very clear. Excellent. So now, notice this. I really did not need to sort these to argue this, right? I mean, the argument that I'm making is that this element has roughly a quarter of elements smaller than it, and roughly a quarter of elements bigger than it, at least. At least a quarter smaller, at least a quarter bigger. Do you agree? And it's the median of the medians. In order to find the median of medians, do I need to sort the entire list? We don't know. I mean, maybe we have to sort it, but that's just a recursive algorithm. So let's say I do the following. In order to find the median of medians, I recursively call my selection algorithm on a smaller set, which is, how large is it? N over 5. So from my problem of size n, let's suppose I'm able to solve the median of medians on a problem of size n over 5. Okay? That seems a massive reduction, right? I'm just doing my recursive algorithm on 20% of the size of the problem. And if I use that as my pivot for really what my interest is in finding an element of size k, of rank k. I'm not interested in finding the median of medians. The whole purpose of finding the median of medians was maybe this is a good pivot element. Let's try to understand, is this a good pivot element? Okay. So okay, so if we use M as pivot element, okay, then what happens, I will split it into two parts. My n is sitting here. This is sitting here. This is less than n. This is greater than n. What can you say about the number of elements here, based on what we have observed right now?
At least a quarter.
It's at least a quarter. At least n by 4. What can you say about the number of elements?
Same.
At least a quarter. Now, I don't want lower bounds, I would like an upper bound. If you tell me both of these facts, what upper bound can you say? So,
75.
3 n by 4. If at least a quarter are here and at least a quarter are there, neither of them can be bigger than 3 n by 4. Okay? And in fact, you can be a little bit more, it's actually a little bit more than that, because you can be more, notice that it's more than a quarter, right? It's not exact, it's in fact slightly more than it's half of 3 by, I don't know, it's something like 3 by 10 or something like that. But let's just work with a quarter. So then it's at most 3 n by 4, and this is also at most 3. So if we were to, so now you understand what's going on. We are recursively, we are going to first do these groups of 5, then we are going to sort, and we are going to find the medians of, so you can find the median of each of them, that's easy. We are not going to sort the medians, instead we are going to call recursively our selection algorithm to find the median of these medians, that's our answer. Then we are going to do the pivoting. Now we are going to do our selection recursion, where we want to find an element of rank k, either on this side or on this side. Okay? So now there are two recursions. You understand? One recursion was to find the median of medians, and the second recursion was to find the actual element that I wanted. Okay? Okay. So before even writing down this algorithm, let's see whether all of this is worthwhile. Okay, viewer. So let's write here just a sense of what the recurrence will be. So if you're, as usual, we will have some base case. So the base case would be once it's smaller than some value. Let me put it as t of 1 equals 1. We might change the base case, because if it's fewer than 5 elements, then we don't want to break it into groups of 5. We will just do the calculation. So our base case would be more like t of 5. Okay? But let's not worry about that, the base cases. So let's see what's happening. T of n, what are we doing? First we are sorting all of this. Sorting each of the group, we are breaking things into groups of 5. That takes linear time. We are sorting each group of 5, each group. That just takes constant time. We are doing it n by 5 times, that takes linear time. So I'm just going to write down that as n. This is groups of 5 sorting each group. What do you do after that? We find the median of these n over 5 medians. Okay? So that's a recursive call. So that's t of n over 5. You are calling the same algorithm on a problem of size n over 5. What do you do after that? After that, what we are doing is we are partitioning into two parts, less than and greater than. What's the time for that? Linear, because we're just comparing every element, and if it's less, put it on one side, greater. Then we are making a recursive call on whichever side our element happens to lie on. What's the worst case possibility for the larger side? 3n by 4. So to be really precise, we are saying that t of n is less than or equal to n plus t of n over 5 is n plus here. Yes?
You
were saying that that's not a correct number though, because it's really something like.
So, but you agree that for less than equal to, that's the correct number? You're absolutely right. You could be more precise by putting something better, and that will be a tighter. Okay? But I'll tell you, we will go over it as to why it's not that important for us to get the correct form. Is that clear? Okay. Now this is a recurrence form we have not seen before, other than in the problems perhaps, but we have not seen before, and certainly you cannot apply something like the master theorem to this because it doesn't have the same. But let's just look at the right hand side. The right hand side is you have 2n plus t of n over 5 plus t of n over 4. Let's solve this recurrence first, and then we will go on to write the algorithm down and agree that we understand. So, whoever, of course, designed the algorithm did not do all these calculations and then solve the recurrence. They somehow saw this recurrence and they saw, instantly they saw, this is a good recurrence. And the reason is the same as essentially that. Look at in the recursive call, look at the total size of the problem we are recursing on. It is n over 5 plus 3n over 4. It's two different recursions, agreed. But let's look at n over 5 plus 3n over 4. How much is n over 5 plus 3n over 4? Okay. It is 20. So you get
95.
19 n by 20. And the crucial thing is this 19 by 20 is smaller than 1. So from a problem of size n, we have brought it down into something that is 95% of n. It doesn't seem like much, but you keep doing that 95%, you go down very fast. Okay? And since this ratio is less than 1, you get this behavior is very similar to that behavior with alpha equals 19 by 20. Okay? So if you solve this recurrence, you'll basically get the t of n equals big O of n. And this is why the 3 over 4, as long as it's less than 3 over 4, it's fine. Yes?
I didn't know that t of something plus t of something could be the same as t of t of something.
It's not the same.
Okay.
Right, absolutely. It's not at all the same. We should be very careful. So we're going to, this is just the intuition.
Okay.
We're going to establish it right now. Okay? How do we establish something like this? There are two ways you could do it. One is you could guess that, oh, it's actually now linear. I'm going to prove it that it's linear. Let's try to prove it that way because it's a good way to see it. So I'm going to prove by induction. Okay. And again, if you were to really be very careful to prove it by induction, you have to make sure that you put all the floors and ceilings and everything, because it doesn't make sense to prove by induction without requiring that everything be an integer, because the induction is happening on integers, right? I'm not going to be careful here, but one that really has to be, you have to be very careful when you're proving by induction. So, you need to put floors and ceilings. We'll also prove it using the recursion tree approach. Right? So let's say that, so in the base case, in this case, of course, since we are dividing it by 5 and 4 and things like that, the base case would be less than or equal to 5. So, or if n is less than or equal to 5, our algorithm would simply is some constant this is the base case. When you're trying to do the induction step, we will assume we are trying to prove the following. Let me write down more carefully what I'm trying to prove. We will prove T of n is less than or equal to c times n for 1 for some constant c that we will pick in a moment. But once we pick the c, we have to keep the same c. Okay? So you want to make sure that this constant c is picked correctly. So base case would be for n less than or equal to 5. P of n is going to be is less than or equal to c times n. Just choose the c. Gives your bound on c. It tells you how large c has to be. Induction step. Okay, we will assume the claim for less than or equal to, let's say, we are using n. Suppose claim true for n less than or equal to p. We are going to now prove the claim for p plus 1. Or if the claim be true for n less than p, we are going to prove the claim for p. Well, t of p is less than or equal to p 2p plus t of p over 5 plus t of 3p over 4. That's what's given to us. By induction hypothesis, t of p over 5 is less than or equal to c times p over 5. C times p over 5. 3p over 4 is less than or equal to c times 3p over 4. Okay, and I just simplify this. So we'll take p out. We get 2 plus c over 5 plus 3c over 5, that is 19c over 20. Okay? What do we want this to be? We want this to be less than or equal to c times p. Right? So we wanted this to be less than or equal to c times p. So when is this less than or equal to c times p? If c is greater than or equal to 2 plus 19c over 20. If c is greater than or equal to 2 plus 19c over 20, and that means c is greater than or equal to 40. So we just choose c to be greater than or equal to 40, and whatever we get for the first 5 elements. For the first 5 values of n, we will get different conditions for c. We will pick whichever is the bigger one, and so that's basically the question. Okay. Yes.
I have a question about
Yeah.
the grouping and sorting.
Yeah.
You said it takes theta of n time. So is it like grouping in 5 and then sorting all the groups?
Yes.
So isn't it same like merge sort where we
No, the reason is you're grouping into 5, and we are sorting each of the groups, but we are not doing anything after that. In merge sort, you would then merge, but you're not merging anything, because if we start merging, then we will end up doing the same thing as sorting, and we don't want to sort. Right? We are not merging at all. It's just grouping into groups of 5, and we are sorting each group and setting them aside. Then we pick just their midpoints, the medians, and we recursively call their medians. I'm going to write down the algorithm fully in a moment. But before I do the algorithm again, just to reinforce it, let me just show you how to analyze this recursion using recursion tree. Okay? So, Okay, so what is the recursion? The recursion is T of n equals 2n plus T of n over 5 plus T of 3n over 4. So we'll do the recursion tree approach. We'll have 2 times n here. Okay, remember we'll write down this as T of box equals 2 box plus T box over 5 plus T 3 box over 4. Okay, so you get 2n, and then you have there are 2 children. One has Tn over 5, the other has T3n over 4. You agree that this is exactly the sum of these 3 quantities, right? Then you open up T of n over 5. So when you open up T of n over 5, what do you get inside? 2n over 5. So it's T of n over 5 is 2 times n over 5 plus T of n over 25 plus T of 3n over 20. Similarly, T of 3n over 5, 3n over 4 is T of 3n over 4 is 2 times 3n over 4, which is 3n over 2 plus T of 3n over 4 times 1 over 5, T of 3n over 20 plus T of 9n over 16. Okay? Is that clear? What we have done? We've just gone over. Yes?
Can you explain the reason why you add n by 5 for the tier equation?
Why did we get this in the first place?
Yeah, for the middle, yes.
Okay, so this is the recursive talk to meeting. I'm going a little bit backwards, this will become very clear in just a couple of minutes. Okay? So this is all coming from the algorithm.
Yeah, I see. So you divide 8 by 5, so there are going to be n by 5 groups.
Medians and n by 5 median. Then we're going to find the median on each of them.
Yeah, so
Now we have n by 5 medians. We put all of them into an array.
this is going to be calculated using the n by in the first element of the game.
Yes, so that's all n.
Yeah.
But then we have to find the median of these n by 5,
Oh yeah, so this is going to be
a recursive talk.
for all of the n by 5 groups.
For the median of the n by 5 to find their medians.
Okay.
Okay? It will become clear in a moment. Yes.
Could you just explain as well why you did 2n over 5 rather than n over 5? I mean,
Oh, the reason is we have 2 times box here. I mean, the reason is we have this 2 here. Okay? So just look at what's going on. So what is T of n over 5? Just let's follow this. What is T of n over 5? 2 times n over 5. So whatever term is here, that's the term that will go in here. Okay? Now you might ask, okay, why did we put the 2 here? Why don't we just work with this? Because we are ignoring constants. Sure. It depends upon how you write the recurrence. If we are not being precise on the constants, so ultimately whether you put the 2 or not, it's not going to change your theta notation.
right. Okay, so in this circumstance, you just didn't ignore that constant. For 2.
Yes. So I think once you are given this recurrence, if you're trying to solve it, then you should keep the 2. Whether you would say, oh, I'm going to ignore the 2 and this is the recurrence I'm going to solve, that's a separate story. But once you have written down that as the recurrence, you'll have to put the 2 everywhere. Okay, yes. Was that a question?
No, I think I answered.
Okay. Was there any other? Yes.
On the right hand side of the page, why is it 3n over 20 instead of 3n over
half.
On the right hand side.
This one or this one?
That one.
This one. Well, let's just put it. If I put box to be 3n/4, what do I get here?
Aren't you getting 3n/2, and then you're plugging in n/5?
No. So I know what you're asking. The reason is I put this in the T, inside the T.
Okay.
If I were to replace it by a node, that's going to change.
Okay.
All I'm doing is, all I did was, you remember what was here? Here was T of 3n/4.
Yep. Okay. I see.
Okay, all I did was this. Now if you open these things up, okay, so now you open this. What is T of n/25? It has, again, two things coming here and this, right?
Okay.
Inside this, what will come? 2n/25. When I open this up, I would have 2 times 3n/20, so 3n/10, and maybe that explains your 3n/10. Um, 9n/8. Okay, and we can keep on going, but let's see whether there is a pattern here. So this adds up to 2 times, and this adds up to 4 plus 15, 19, 19n/10. So 2 times 19/20. Understand? This one will add up to, we should be able to see that, 2 times 19/20 whole square. You can verify that. Okay? And I'm just guessing based on what this is going, but you can calculate that. So it's going down by a factor of 19/20 all the time. So if you were to run this whole recurrence, you will get T of n is equal to n 1 plus 19/20 plus 19/20 squared, and so on. What about the number of levels?
Log 20/19.
Yeah,
I don't understand why it's
you don't understand why we did this? Okay. All I meant to say was that you add these up, you will get this. Okay? But let's try to verify it since you're asking. So you take 2/25 plus 3/10 plus 3/10 plus 9/8. You get 200. 8 times 2, 16. Plus 20 times 6, 120. Plus 9 times 25 is 225. So you get 225 is, so you get 361. So it's 361 by 200. 361 is 19 square. If you put a 2 up here, then it's exactly the same. Okay, so what is the height of this tree? Well, you notice that things are happening at different rates. If you go left, everything is being divided by a factor of 5. If you go right, everything is divided by a factor of 4/3. Everything is multiplied by a factor of 3/4. Okay? So, what's the shape of this tree? Does it look like this? Or does it look like this? It looks like the left one because you're dividing it by 5. So it's rapidly finishing up. Okay. Alright, but the point is it doesn't matter which side we look at, because this is a geometrically decreasing series. Even if you take it all the way till infinity, this is going to be bounded by 20. You see that? This quantity is always bounded by 1 over 1 minus 19 over 20. This is a geometrical series with a ratio of strictly less than 1. That's bounded by 1 over 1 minus r. So this is less than or equal to 40 times 10. Notice the same 40 that we had in the other case. So it's less than or equal to 40 times n. Of course, it's at least 2n, the way we have written this down. So T of n is theta n. Now you might say, oh, there is a huge gap between less than equal to and greater than equal to. I'm saying less than equal to is 40n, greater than equal to is 2n, that's a big gap. Surely there is a big gap. Part of the reason is we were imprecise here. We should have been maybe more careful. We would have gotten a better constant there, and so on. But our thinking right now is this a linear time procedure or not? And we will be happy with that. Okay? Okay, good. So let me just write down the algorithm formally so that everybody gets what's going on here. And I'll leave this picture here so that okay, so deterministic algorithm for selections. So let's call this select. You're given an array A. It has n elements, and you are looking for an element of rank K. That's your selection routine. Okay? What do we do? Well, if n is small, if n is smaller than or equal to 5, then you just sort it and return whatever you need. Okay? Then this is the base case. If you just have 5 elements and you're looking for the third smallest or fourth smallest, you can easily just sort the entire array and return the third smallest term. Sort A and return element of rank. Okay? Otherwise, we are going to do a few things. What did we first do? We are going to group things into groups of 5. Group the elements into groups of 5.
So is this 5 necessary or can be any arbitrary number?
Good. We'll take a look at it after we have written this down. So group elements. And I'm writing this informally, but people can easily, should be comfortable in translating that into code if need be. Okay? And we are doing this arbitrarily. We don't have to. We can take the first 5 elements. That's the first group of 5. Next 5. This is unsorted. So just take the A 1 through 5, first group of 5. 8, 6 through 10, second group of 5. Okay. Find a sort each group and find median in the group. Store the n over 5 medians in array B. Okay? Is that clear? So if you have, so the way we do it is we have these groups of 5. We sort these 5. we separately sort these 5, we separately sort these 5, we separately sort these 5, we separately sort these 5. Then we take the middle element, the middle element, the middle element, and put that into a different array. B. Any questions for this? Okay? All right. How do you sort each group of 5? It's just 5 elements. Do insertion sort, do whatever the basic sort that you can think of. Okay. Now what do after this? Once we have all the medians in B, what do? Find the median of these medians. Okay? So this is the recursive call. So we have to call back, select. And we are storing that in our element M. So let's write as M equals to select B n by 5. What k should I pass to the selection? It's n by 10. It's the median of these n by 5 elements. So it's n by 10. Okay? Literally, this is just a recursive call. It's very straightforward to go just a call to select. Then what do? Now that we have identified that this has returned us one element M. What are we going to do? You're going to take this array A and put it into 2 parts. Let's call it A left, A right. And each would be an array of elements less than equal to and greater than. Okay? So, partition. Okay? Partition A into AL. Partition A, AL equals elements less than M, AR equal to elements greater than. Okay? Is that clear? So let me draw a picture here and we'll finish the rest of the algorithm here. So M is here. This is less than M, so A now. This is greater than M, so A. This is what the picture looks like. Okay, assume that all the elements are distinct. Okay, if they are the same, it's easy to extend. Okay, so is that situation clear? What's now, remember, what is our original problem? We want to return an element of rank k. So far, we haven't even looked at k. All we have done is on the median of medians and then partition, right? Okay, now what do? Now we have to compare with k, right? So at this point, what do you think we should do? Rank of n. So we could compare, we look at the rank of n. What is the rank of n? What is the rank of n?
Greater than n by 4.
That is true, but once you have partitioned it, you know the rank of n? Yes. So what is the rank of n? No, not n by 2. The number of elements in AL plus 1. We know the number of elements in AL. We have created the array. Right? So we know the rank of n. So let's give a name to that. 9. So let's take use L to start let J be the size of AL plus 1. This is the rank of n. Okay? Now what do? We are at J, so we found the rank of M. If you're really lucky, the rank of M is exactly K. So we check this J is the same as K. If J equals K, then we know what we need to do. We simply return M. If K is less than J, then where do we have to search? You have to search on the left hand side. So what do we return? We have to fill the 3 parts. Which array do we call on? AL. How many elements does that array have? It's J. What rank are we searching there? K. Because the kth element in the whole array is also the kth element in the first half because K is smaller.
J minus 1.
Is it J minus 1? You're right. Thank you. J minus 1. Okay? By the way, if you're writing this piece of code, it was not super essential for us to include this n because it was included in the array to some extent, but that's not really important. There might be more efficient ways to write it. If K, the final case is if K is greater than J, then what do we return? We return select AR. How many elements does AR have? N minus J. Now, what's the rank in AR? If K we are looking for, this is K. If this is K, then what's the rank, what's the position of, is the kth element we're looking for here? So it's K minus J.
N minus J.
Is that right now?
K minus J plus 1.
N minus J, N minus K.
Return.
No, I think it's K minus, so J is, this is J.
Yeah.
And we are looking for the kth element in the overall list.
Yeah, no, it's N minus J
Ah.
and N minus K.
Thank you. Okay, you will be just double check whether we are receiving a -1 or +1 or something like that. But that's the output. Okay. Okay, let's quickly visit a couple of questions that came up. So one question was about 5. Let's try the following. Okay. So one reason, by the way, we took 5 is it's an odd number. So it splits things evenly. So it's symmetric. What is greater than and less than is sort of symmetric. If you don't have 5, if you take like 4 or 6, then the median itself you have to now figure out, should I take the upper one, should I take the lower one, and it's all the same. So that's one of the reasons. So let's try a different odd number. Let's try 7. So if you had 7, you have a rectangle and here you have 7 elements, and here you give median. What can you say? So actually, even for 5, let's try to be more precise for 5.
It's 3/10.
Okay, so the more precise answer for 5, as somebody mentioned, is 3/10, right? Because this is, if you just take this whole rectangle, it is 3/5, and we are taking half of that, so it's 3/10. So you could rewrite your recurrence as T of n is less than or equal to 2n plus T of n over 5 plus T of n over n. So that's it, 3. sorry, 7n/10. Because each side is 3/10, that means no side is bigger than 7n. And again, if you apply the same calculation, you get 1/5 plus 7/10. This would be 9/10. Instead of 19/20, we would get 9/10, which means the constant that we will get there would be 10. So, and that'll be 20. So it'll be a much better analysis than. Okay. Let's see what will happen if you do 7. So if you do 7. Same argument. So if you do 7, how many elements are guaranteed to be on this side? 4. So there are 7 elements, right? So how many elements are guaranteed to be on this side? So this is 4 out of 7. So half of 4 out of 7. So 2 out of 7. So we will get each side is at least 2/7n. That means each side is at most 5/7n. So you would get T of n is less than equal to whatever this n is. Let's measure this to n for now. T of n/7 plus T of by T of 5/7. What is the sum of these two? 6/7. So if you do the ratio there, you will come out to 7, which is better. However, there is a trade-off. You see the trade-off? Each of the groups is now size 7. So it's going to take you longer to sort them. If you're going to sort them, it's going to take you longer to sort them. Of course, there are fewer groups. But if you are sorting each of the groups, sorting n/7 groups of size n is more expensive than sorting n/5 groups of size 5. Yes?
So shouldn't the number we're picking, 5 or 7 or whatever, be dependent on the size of n?
The problem is, no, if n is large, it doesn't matter. One of those two will give us better performance. Okay? In terms of theta notation, they both work exactly the same. Okay? So, as long as if n is large, one of them will give better performance. The particular depends upon the particular routine you use for sorting each group. Maybe the particular way you apply partitioning. It depends. I think 5 to 7. The larger you go, if you go to 11 and 9 and so on, you end up spending. This 2 becomes bigger and bigger. Yeah, this 2 becomes bigger and bigger, then you're trading off 2 quantities. The 6 you're getting from here versus the 2 you're getting. Okay. So any constant greater than or equal to 5, you'll get the same behavior. And it's worth for you to try to just do a couple of more. It's interesting, and it will be instructive for you to try yourself. What happens if you choose 3? Okay. So if you only have 3 elements per row, what do you get? Okay, I will let you do the calculations. Yes.
Thank you. In the algorithm there, it's just not clear to me where you are selecting elements to return. I see that we're making recursive calls to some, in 11 and 12, and then 7 calls m to be equal to a recursive call.
Okay.
But the only thing that we're returning that isn't a recursive call is 10. And 10 seems to be,
No.
which is
11 and 12 too. Yeah, right. Correct. So the only element that is finally returned is m.
But m is...
No, it's a two places. One is here. One is here.
Okay, so we have to get it, everything has to go down.
Small enough.
Got it, thank you.
Yes.
Since we know if the big selection algorithm it's not the worst case. It will always be mid or algebra. So can we do the partition like every time we just randomly pick 3 elements, we just pick the middle one, then it will always be mid.
Yes, good.
Simpler than this one. Right?
Much simpler.
Yeah. Can we do that?
But it's not guaranteed to always do linear. In practice, that will be a better algorithm than this. But if you want to come with a solution that works no matter what, that
Even
choice.
the real time is longer than this one. Maybe
No. So if you were to do a randomized selection, which we went over, or some version of randomized selection, you would have an expected time which is linear. With very good probability it will be linear, but on rare occasions it won't be.
But right now, we avoid the worst case.
No, you never. If you're doing randomized, you never avoid worst case. In the sense that you don't avoid the worst case choice of the random.
Because we pick 3,
Even if you pick 3,
and then we pick the medium one.
but
That's
even,
not the
but
worst case.
your 3 that you pick might be all the first 3 elements.
Yeah, but that's not the worst case. Worst case should be the largest one and the smallest one. I only pick the medium one. That's not the worst case.
No, but for that algorithm, the worst case is if you pick the 3 to be the smallest ones, and then the median, you pick the median, that's fine. But the worst case would be that the median just happens to be. Maybe we'll talk about it. Okay. Yes.
In 7 we are already sorting the middle element, and again in 10, 11, 12 we are using that m we found as a pivot, and again putting it in a like left is less than right is.
Right.
So haven't we already sorted? So is there a way that we can skip that?
Yes, you could. That's a very good question. You could do since you've already sorted, perhaps you just look at the. You have to be careful because you can compare the middle element with each of these, and once it is smaller, you could already put these on one side. Once it is larger, you could already put this on the other side. But then you still are allowed to compare each of these.
Yeah, that.
Yes. Yes.
You told that you take a larger value, the time spent on sorting the subarray itself is large. If you take n as 2, what will be the relation? Because anyway your arrays become smaller, and in that sense, time spent on sorting.
If you take 3, meaning
2.
well, 2. The problem is what is the median of 2 elements?
Okay. Technically the first element.
Yeah, I think then it's not worthwhile doing that. So 3 is an interesting case to consider. 3, you're doing it very fast. 3 elements quickly can find a median because you just have to do the comparisons. But do we break the problem down to small enough that you have to write down the recurrence to see whether you're getting benefits of it? Okay, we'll stop now. We have a quiz. So what I would request people to do is spread out to the extent possible. I think especially in the back rows, if you could. So can you just try to switch maybe one level here, and maybe you move to the right and things like that. refer to any material other than some that request. Okay, so it's closed book, closed notes, really, and you can. There are 2 questions, one on each side. So make sure you look at both of them, and just write clearly and legibly. And the grading will be based on both clarity and correctness. Make sure you write your name. You have until 11:30 to finish. And if you are done before, you can give me the quiz and take off. same hand, right? In problem 1, I think a number of people are asking this, but it's just n men and n women. Same number of men, same number of women. It's required that you need to have at least 2 men and 2 women. You have 5 minutes. Thank you. Thank you. Oops, sorry. Yes.
So I wrote this, but then I scratched it out, and then I wrote the answer up here. Sorry.
I'm trying to get this through. Whatever it says, everything is there.
Professor?
Sure, I'll take it. Of course. Thank you.
一个他为什么要去找一个 medium？ 你说为什么找这个？你说随便找一个，对啊，就随便，那随便找一个也没有办法保证它一定能分。没有，他不是说嘛，你要说分成那几个题目嘛，都是 average case 都是找出那个极端情况一和典型例。哦，不一定啊，你如果 n 减到2也是正常的。但是这个如果证明嘛，就是那个方法。 你的expectation 应该是一开始都是不错的，你在分的时候这边是2分之 n 对吧？100分，对，100分，没关系，这个